Welcome to the course on An Introduction to Information Theory. So far we have been talking about discrete random variable and entropy associated with discrete random variable, right? Now today we are going to talk about entropy for continuous random variable, and that is known as differential entropy. So it's the entropy of continuous random variable. So in this class we will define what is differential entropy, and we will prove some properties of differential entropy. So let x be a random variable whose cumulative distribution function is given by f of x. If f of x is continuous, then we say the random variable is continuous. So if the derivative of f of x exists and is defined, which has the following property, that integration from minus infinity to infinity is 1, then f of x is known as the probability density function of x. The set over which f of x is greater than 0 is known as support set of x. These definitions have a very similar to the definitions we had for discrete case. If you recall, for the discrete random variable we defined the support set as the set where probability p of x is greater than 0. Now differential entropy of a continuous random variable is defined as follows. So it's defined as minus of integration of this probability density function, log of probability density function, integration over this support set of this random variable. So this is how we define differential entropy. If you recall, for discrete random variable we define entropy as minus of summation p of x log of p of x. So this is very similar to that. Now let us take an example. Let x be a normal distributed random variable. So the density function phi of x is given by this pi sigma square exponential minus x square I 2 sigma square. So this is a zero mean variance sigma square normal distributed random variable whose density function, can use the term f of x, or I am using here phi of x, is given by this expression. So what is the differential entropy? So differential entropy is defined in this particular fashion. So this can be written as phi of x. Now if we take log of phi of x, we get log of this term, and we get log of exponential will be just this term. So we get minus phi of x, and log of phi is given by this expression. So this is this, and log of 1 by under root of 2 pi sigma square, that is this. Now this can be written as minus phi of x minus x square 2 sigma square d of x, and minus of minus natural log of 2 pi sigma square phi of x dx. So this minus minus becomes plus. This integration phi x x square 2 sigma square dx, it is nothing but expected value of x square by 2 sigma square. So this first term that you see here is nothing but expected value of x square by divided by 2 sigma square, and this, there is no x here, so this is a constant. So if we integrate over phi of x, we will get 1. So this term is nothing but given by this. Now what is the expected value of x square? That's given by variance of x plus expected value of x whole square. Now what is expected value of x? That is 0. So this term is 0 and variance is given by sigma square. So this is variance sigma square. So then expected value of x square is given by sigma square. So sigma square cancels out. What we'll get is half. So half, I can also write it as half is half of natural log of e, and then I can, this is of the form half of natural log of e plus half of natural log of 2 pi sigma square. So this is log a plus log b, which can be written as log a times b. So then this can be written like this. Now note, we were talking about natural log, so this is in nats. If we take log to the base 2, then the units will be bits. So the differential entropy of a 0 mean Gaussian random variable with variance sigma square is given by this expression, half of log 2 pi e sigma square. Now if x1, x2, x3 are sequence of random variables drawn independent and identically distributed according to distribution f of x, then 1 minus n log of f of x1, x2, x3, xn, this converges to differential entropy in probability. Now the proof of this is very similar to the proof that we did in the discrete case. This follows from the weak law of large number. So this can be written as product of fxi. So when you take log of product term, you get summation. So then you will get summation of minus 1 by n log of fxi, and that by weak law of large numbers is basically expected value of this, which is equal to differential entropy, and this converges to differential entropy in probability. So we are skipping this proof because it is very similar to what we have done earlier. Now for an epsilon greater than 0 for any n, we can define typical set with respect to this density function as follows. So typical set is defined as x1, x2, x3, xn belonging to this set such that minus 1 by n log of f x1, x2, x3, basically it is close to the true differential entropy and the difference is within epsilon. So very similar to how we defined typical set, we for the discrete case, for the continuous random variable also we can define typical set. Now in case of discrete random variable, we define how many such typical sequences are there. The similar analogous thing for continuous random variable is what we call volume of a typical set, volume of a set. So volume of a set is defined as this. Volume of a set is defined like this. So analogous to the number of typical sequence, here we have the volume of the typical set. Now typical set has following properties: that probability of typical sequence for very large n, that is greater than 1 minus epsilon. Now again this follows from AEP property, that we know that this converges to differential entropy in probability, and this establishes the proof that probability of this typical set is greater than 1 minus epsilon. The next property which says the f of x lies between this and this. Now this can be proved from the definition of typical set. So if you go back and look at the definition of typical set. We define typical set as, so this empirical differential entropy, the difference between that and the true differential entropy, the absolute difference should be less than equal to epsilon, right. So depending on whether this term is greater or this term is greater, because we are taking absolute difference, we will get either this inequality or we will get this inequality. Again, the proof is very similar to the proofs we have done many times before, so I am just skipping the details of the proof. The next property that we are going to show is the volume of the typical set is upper bounded by this. Now we know that if you integrate this density function over the support set, we will get probability 1. Now if we integrate over typical set, then since typical set is subset of this S of n, so we get here this greater than equal to, because we are integrating over a smaller set. So that is why this greater than equal to sign comes. Now we know that this density function is lower bounded by this. Okay. So if we plug in this lower bound on f of x1, x2, xn here, what we get is this, and that is why we are writing it as greater than equal to. Now we can take this out, and if we integrate it over the typical set, what we get is the volume of the typical set. And so volume of the typical set multiplied by this is less than equal to 1. So from here we get volume of typical set is upper bounded by this 2 raised to power n times differential entropy plus epsilon. Similarly, we can prove that volume of a typical set is lower bounded by this. Now this follows from, we know probability of this typical set is greater than equal to 1 minus epsilon. So 1 minus epsilon is less than equal to this probability of typical set, which is given by this expression. Now we know the upper bound on this f of x1, x2, x3, xn. This follows from this property. So we know the upper bound on f of x. Now if we plug in the upper bound of f of x1, x2, xn here, we get here less than equal to, and subsequently we take this out, integrate it over the typical set. What we get is volume of typical set multiplied by this. This is greater than equal to 1 minus epsilon. So from here we get volume of typical set is at least given by this. Okay. Now what is the relation between differential entropy and discrete? So we are comparing the differential entropy of a continuous random variable with the entropy of a discrete random variable that we get by discretizing that continuous random variable. So this result says that entropy of an n-bit quantization of a continuous random variable is approximately given by differential entropy of x plus n. So let us consider a random variable x whose density function is given by f of x. Now as we said, we want to compare the entropy of the continuous random variable with the discretized version of this continuous random variable. So we divide the range of x into bins of length delta, and from mean value theorem we know that there exists an xi such that f of xi times delta is equal to this. Alright. So then we are considering a quantized random variable, we are calling it x delta, which is equal to xi if x lies between I delta and I plus 1 delta. And the probability that x delta is equal to x is then given by this f of x dx, integrate over this interval I delta to I plus 1 delta, which by mean value theorem is given by f xi into delta. So let us compute then the entropy of this quantized random variable x delta. This is given by this expression. This follows from the definition of entropy. Now Pi is given by fxi delta, so we plug in the value of Pi here, we plug in the value of Pi here. So here we have log of A times B, that form. So this can be written as log of A plus log of B. So then log of fxi delta can be written as log of fxi and log of delta, and this comes here, this comes here. So what we have here is this term plus this term. Now this term does not depend on xi's, and if you sum fx delta I, this will basically be 1. So what we get here is minus log of delta, and this term for small delta approximates to the differential entropy. So we can write the entropy of the quantized random variable to be equal to differential entropy minus log of delta when delta is very small. Now if we assume x to have uniform distribution between 0 and 1 and we take our delta to be 2 raised to minus n, then in this case differential entropy is given by log of A, which is a log of 1, which is 0, and log of delta minus log of delta will be n. So h of delta will be h of x plus h of x minus log of delta, minus log of delta is n, h of x is 0. So then h of x delta will be n. So which implies that basically n bits are sufficient to describe x within n bit accuracy. Now here we have made use of the fact that what is the differential entropy of a uniformly distributed random variable. So if you have a random variable which is uniformly distributed between 0 to A, its differential entropy from the definition h of x is given by minus our support group f of x log of f of x d of x. Now if it is uniformly distributed between 0 to A, it looks like this. So 0 to A is uniformly distributed, so this will be 1 by A, this is my f of x. So this will be minus 1 by A log of 1 by A dx, and this integration will be from 0 to A. So this can be written as 1 by A integration log of A dx 0 to A. So this is 1 by A into log of A. So this will be log of A, and in this case my A is 1, so log of 1 is 0, and that is why I wrote differential entropy for x which is uniformly distributed is between 0 to 1, its differential entropy is 0. One point I just wanted to make which is different for differential entropy compared to the entropy for discrete random variable is, for discrete random variable the entropy is greater than or equal to 0. Here the entropy can be less than 0. For example, if A is a fraction, let us say A is half, then entropy will be in this case will be log of half, which is minus log of 2, which is a negative quantity. So differential entropy can be negative. However, volume of a typical set that is positive. Okay. Next, we are going to define differential entropy for random variable x1, x2, x3, xn. So differential entropy for a set x1, x2, xn whose joint density is given by this can be similarly defined like this. So it's a very straightforward extension of definition of differential entropy for single random variable. Similarly, we can also define conditional differential entropy. So if x and y have joint density function given by this, then we can define conditional differential entropy in this fashion. Again, this is, if you look at the form of this expression, it's very similar to the form that we had for the discrete case. Similarly, we can define mutual information. So mutual information between two random variables with joint density function given by this is nothing but divergence between fxy and the marginals fx and fy, and this can be written as differential entropy of x minus conditional differential entropy of x given y, or differential entropy of y minus differential entropy of y given x. Similarly, we could define the divergence between two densities f1g. This is defined as expected value, expectation taken with respect to f of log of f by g. So this is the divergence between f and g. Now let us consider an example. So we are considering a multivariate normal distribution. So x1, x2, x3, xn have a multivariate normal distribution with mean given by mu and covariance matrix given by x. Show that the joint differential entropy is given by this expression, where this is nothing but determinant of K, the covariance matrix. So since x1, x2, x3, xn follows a multivariate normal distribution, so their density function is given by this expression. Next, we apply the definition of joint differential entropy. So this will be minus f of x log of f of x dx. So when we take log of this function, we will get log of this plus this term minus half x minus mu transpose k inverse x minus mu. So this is what I am writing here. So I have minus half x minus mu transpose k inverse x minus mu, that is one term, and then we had this minus of 1 by under root 2 pi n determinant of k. So we have these two terms. Now second term, if I integrate over f of x, I will just get this, okay. And let us look at the first term. This is nothing but expected value of this. So in matrix form I can write this in this particular form. This is summation over I and j xi minus mu I k inverse ij xj minus mu j. So after I can keep it here, I can combine these two terms. This can be written as expected value of this multiplied by k inverse of this. Next I can write this as kji and kij inverse. So this will be non-zero only for those terms where I is equal to j, and that's basically this, and this is going to be I. So summation over all j, this will give me n, and this way I am getting n by 2. And then this term is coming from earlier, so we get this. Now n by 2 I can write as n by 2 natural log of e, and then I have this term which is half of natural log of 2 pi n and determinant of k. This I can also write as half of natural log of e raised to power n plus this term. So now I have half log of this particular term here. So log of a plus log of b kind of form. So this can be written as log of ab. So this can be combined into this. Now if I write unit in terms of log to the base 2, I get my differential entropy to be this. So for a multivariate normal distribution with mean mu and covariance matrix K, the differential entropy is given by this. Let us take an example. So x and y are multivariate Gaussian distributed, mean 0, covariance matrix given by K, which is this. So we can write h of x and h of y, which is nothing but half of log 2 pi sigma square, and similarly we can write joint differential entropy, which is given by half of log 2 pi square and determinant of k, which is given by this. And now we can write, if you mutual information also as h of x plus h of y minus joint entropy, and this comes out to be this. Okay. Now if rho is 0, which is basically these terms are 0, you can see x and y are independent, and in this case the mutual information between x and y is going to be 0 because x and y are independent random variables. And if rho is plus minus 1, that means they are perfectly correlated, then you can see mutual information is going to be infinite. Now similar to the discrete random variable case, here also the divergence is greater than equal to 0. So divergence between two density function f and g is greater than equal to 0. Again we can prove it in a similar fashion. We take minus of divergence between f and g, which is given by this expression. Now log is a concave function. If you recall, log is a concave function. Log is like this. And from Jensen's inequality, what do we know? The expected value of a function is less than equal to function evaluated at expected value. If it is a concave function, then Jensen's inequality says this. So if we apply, so this is like expected value of this function, log function, right? So since log is a concave function, so by Jensen's inequality, the log of expected value of the x should be more than expected value of the function. So from Jensen's inequality we know this relation holds if f of x is concave. If this is a concave function, then this holds. So expected value of log will be less than equal to log expected value, and this basically is then integration of g over the support set is 1. So log of 1 will be 0. So what we have proved is minus of divergence is less than equal to 0. So if multiply by -1 both sides, we get this. The divergence between two densities f and g is greater than equal to 0. Now similarly, we could define chain rule also for continuous random variables. So differential entropy between x1, x2, x3, xn can be written using chain rule in this particular fashion. And since we know conditioning cannot increase entropy, again this can be very easily proved. We have just now shown divergence is greater than equal to 0, and we know mutual information is divergence between the joint densities and the marginals. So mutual information should be greater than equal to 0, and from there we can prove that conditioning cannot increase entropy. So from the chain rule, which is given here, if we apply this condition that conditioning cannot increase entropy, we can write, we get this condition. And of course this joint differential entropy is equal to this individual differential entropy when these xi's are independent. So I have already given the proof. This follows from the chain rule and the fact that conditioning cannot increase entropy. Only when x and y are independent that this is equal. Now we can make use of this result to prove what is known as Hadamard's inequality. So if we consider a multivariate random variable with 0 mean and covariance matrix given by k. Now if we compute its differential entropy, this will be given by, we have already done this before, this is given by this expression, it's given by this expression, half of log 2 pi e raised to power n determinant of x, and what is this h of xi? This is half of log of 2 pi e kii. So if we compute this differential entropy here, we will get terms of the form, this is half log 2 pi e, this kii form, summation over all n, will get something of this form, whereas this differential entropy is a form half log of 2 pi e raised to power n determinant of this, and this we can write as, so summation of log, this can be written as, this can be written as half log of product from I equal to 1 to n kii, and you have this 2 pi e raised to power n term here. So if you compare these two forms, you have half log of 2 pi en and you have half log of 2 pi en, and since this is less than equal to this, we will get the condition that determinant of k is less than equal to this particular term. Okay. So this follows from two results. One is this one, and second is the differential entropy of this multivariate Gaussian random variable. Okay. Now we will prove some more properties of differential entropy. So translation does not change differential entropy. So differential entropy of x plus c is same as h of x. So this is straightforward to prove. So we have a new variable y which is x plus c. We can write the density function of y in terms of density function of x. Now we can write density differential entropy of x in this particular fashion, and x is nothing but y minus c, so this is given by this, and this is nothing of f of y, so this is equal to differential entropy of y, which is nothing but differential entropy of y is x plus c, so this is differential entropy of x plus c. So what we have proved is differential entropy of x is same as differential entropy of x plus c. So translation does not change differential entropy. So this is the effect of scaling. So differential entropy of a times x is given by differential entropy of x plus log of absolute value of a. So here y is given by a of x. We can write the density function of y in terms of density function of x, and from the definition differential entropy of y is given by this expression. Now we plug in the densities of y in terms of densities of x, which is this, okay, and this we simplify, log of 1 by absolute value of a plus log of f of x of this, and y by a is nothing but my x. So this can be simplified into two terms. One is this particular term and second term is log of a. So you can see basically this will be log of 1 by a. So log of 1 by a is minus log of a, and minus minus that becomes plus, and when you integrate it over the density function, this basically density function will become 1. So you get log of a, integration of this density function will give you 1. So this is log of a, and the next term that you will get is this log of f of x y a, which is nothing but f of x log of f of x. So this is nothing but differential entropy of x. This is log of absolute value of a. So the effect of scaling is as follows. So h of differential entropy of a of x is differential entropy of x plus log of absolute value of a. Now the next result that we are going to show is as follows. So if you have a random vector x with 0 mean and variance given by this, then its differential entropy is upper bounded by half log of 2 pi e raised to power n determinant of this covariance matrix, and equality happens when x is multivariate Gaussian normal distributed random variable. So if x is a random variable with 0 mean and covariance matrix K, we are saying it is the Gaussian multivariate Gaussian distributed random variable which will have the maximum differential entropy. If you recall its counterpart, in case of discrete random variable, it is the uniform distributed random variable which will have the maximum entropy. Okay. Now how do we prove it? So we have been given that mean is 0 and covariance is fixed k. So let g of x be a density satisfying this condition. This is basically the covariance. Let phi of x be 0 mean multivariate distribution which has the same second order moment which is given by k. Okay. Now let us compute the divergence between this density g and this 0 mean multivariate normal distributed phi k. So this divergence between g and phi k can be written from the definition as g log of g by phi k. Now this can be written as minus differential entropy of g minus integration of g log phi k. Now log phi k is of quadratic form, right? Log phi k is of quadratic form, and we have been given that x and phi k has the same covariance. So this is, they have the same this thing. So integration of xi xj phi k dx is same as integration of xi xj gx dx. So then this term g of log phi k will be same as phi k log phi k, because this has a quadratic form. Log of phi x will be a quadratic form, xi xj form, and we know that integration of gx xi xj, this is same as integration of xi xj phi k. So this is equal to this, and that's why we are able to write it like this. Okay. Now this is nothing but plus of differential entropy of this 0 mean multivariate distribution. Now this is greater than or equal to 0, that means h of phi k is greater than or equal to h of g. So in other words, it is a multivariate normal distribution random variable which will have the maximum differential entropy. So with this we will conclude our discussion on differential entropy. In the next class we will talk about Gaussian channel. Thank you.